So in this video, we're going to take a look at what do we know about this separation of variables technique and when do we run into problems with using it. So at the very top, it's just a reminder of the last problem that we worked out, which was, it turns out that y equals 0 is a solution to this. And so it definitely is a solution, even though you wouldn't necessarily notice it from the analytic solution method, the separation of variables method. And we know it's a solution because it works when we sub it back in. And so if something works when you substitute it back into the differential equation, then it's a solution. And so we also know it's a solution because it's an equilibrium solution. Right? Equilibrium solution, if you remember, that's where dy dt equals 0. Right? So this leads us to our first kind of issue with the separation of variables, and pretty much any analytic method for solving differential equations. So issue number one is sometimes it turns out general solutions that we obtain analytically do not easily predict, or another way you could say it would be easily show all solutions. Sometimes we run into situations where equilibrium solutions especially are kind of sitting there in plain sight, but we don't see them because we get lost in the algebra and the calculus. So that's the first issue. This is what I like to call the kind of forest for the trees. You know, sometimes you don't see the obvious solution because you're so busy getting down and dirty with the algebra and the calculus. Issue number two, well, here's an example of issue number two. I want to solve this differential equation. And I can look at it and say, hey, cool, I'll use my trick. But notice right here we have two terms, and it's not factorable. Which means this thing is not separable. So we can't solve it analytically yet, because we are going to get there. But right now, this equation is off limits to us. We don't know how to solve it. Now, Maple knows how to solve it. So I can step into Maple and say, hey, would you solve this for us? What is, let me scoot down here, what is desolve y prime equals y of x? Actually, I don't even have to do that, y plus x. And Maple says, yeah, I can do that. And you notice, it doesn't look all that difficult. It doesn't look like it's that complicated. But somehow there's a 3 terms to the solution, but only one of them has a constant due to integration. So why do these 2 terms not have a constant due to integration? Well, at this point, we don't know. So switching back to the notes page, we know Maple can do it. Maple says the solution is something like y of x equals negative x minus 1 plus some constant times e to the x. So it is doable. It's just not doable by us. We don't have the tools. So it's kind of like when you learned how to solve quadratic equations and the world seemed to be your oyster, and then somebody put a cubic in front of you and you're like, no idea, I don't know how to solve that. I can't use the quadratic equation, at least not right away. So we're going to learn different methods. But right now, that one's off limits. Here's another one. This one is an example of the third issue with the separation of variables. Is it separable? Well, I don't know. Let's take a look. Looks pretty complicated over here, but everything is in terms of y. So we can think of this as just kind of multiplied by 1. And so that's my function of t. So this is separable. And so you think, yay, it's separable. Shouldn't be any trouble. So I'm going to multiply both sides by, or excuse me, divide both sides by this whole thing, y over 1 plus y squared, or multiply by its reciprocal. And so on the left-hand side, I'll have the integral of, see, it'd be 1 plus y squared over y dy. And the right-hand side would just be the integral of 1 dt. I got the right-hand side integral. The left-hand side integral is a little bit more of a pain in the butt. This becomes the integral of 1 over y dy plus, well, I'm breaking up this thing into two separate fractions, decomposing it. And so this becomes y squared over y, or just y dy. So I have two integrals on the right or left-hand side. The right-hand side is just the integral of dt. So not too hard, not too difficult. So this becomes the natural log of the absolute value of y. And I'm going to group these constants together, plus 1/2 y squared plus a constant on this side. The other side is just t plus a second constant. And so far, that's not so bad. But what about solving this thing for y? If you had to solve that thing for y, you'd have to both exponentiate to get it outside of the logarithm, but then that would put it in upstairs of an exponential if you did that. So the problem that we're going to run into is solving this thing for y is no fun. Forget it. There's no way we're going to do that. And so oftentimes what we'll do is we'll just stay in explicit form, or the implicit form, excuse me. And so that's not fun. We didn't actually solve it for y. And so the problem is there's nothing that I can plug back into this differential equation because it's not solved for y by itself. So the trouble that we're going to run into here is, unfortunately, implicit form becomes really difficult to verify, really difficult to check. And, as you might be guessing, there's a way to check this in Maple, but for us, for algebraic purposes, this is going to have to stay in implicit form. And just for giggles, let's see what this looks like when we try to solve it using Maple. So I'm going to desolve, and I'm desolving. Sorry, my dogs are in the room deciding they want to shake their heads here. Y of t with respect to t equals, the right-hand side is y of t divided by 1 plus y of t squared. Close my parentheses. And so just to double check, that's indeed what we're doing. Yep, that's the differential equation that we're messing around with. And let's see what Maple makes of it. Check, 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 check. Uh-oh. Typically, when you run into a differential equation that when you solve it in Maple, it gives you the name of a person, that's usually a sign that you are punching above your weight class. So you can see right here, we've got a e to the some power involving a Lambert's W function. And of course, we don't know what that is. You could look it up if you wanted to. What is this thing right here? You could do a search in Maple and ask Maple what it is. But pretty much guaranteed, if you've never heard of it before, it's probably complicated enough where you're not going to understand it. So Maple found a way to write it in explicit form, but we can't. This is actually in terms of an integral. So it's not going to be very helpful for us to do that. So Maple can solve it explicitly, but we can't. We don't have the chops. So this third problem is sometimes you have to leave your solutions in implicit form, which makes it really tough to check the answers. And then down at the bottom of this page, our last example. In the previous one, we were actually able to do the integrations. That wasn't the hard part, but it was just writing it in terms of y. In this case, we start with, on the left side, we've got a dy dt, and then this is just a function of y. So it's times 1 again. So yay, we can use our separation of variables. So this is a separable. I don't know why I was making my exclamation points there, but this is a separable equation, so I can write it as the integral of dy over secant of y squared. And then the right-hand side would be just the integral of dt. And if you're noticing, this is the same thing. 1 over secant is the same thing as cosine. So this is really just the integral of cosine of y squared dy equals the integral of dt. Now the integral of dt, that's easy. But what about the integral of cosine of y squared with respect to y? You might be thinking, oh, it's just, do u substitution. But u substitution won't work here. Because if you let y squared equals u, then dy is 2y dy. du is equal to that. This is ugly. The problem is that this becomes a major, major frowny face. Even with tears, you drive yourself to drink with this one. This is a nasty, nasty little integral. It turns out that the integral of something so innocuous sounding, the cosine of y squared, actually requires a Taylor series expansion in order to write this thing. You have to use integration by parts multiple times. It's really ugly. Let me show you what Maple makes of it. If we said, hey Maple, will you solve for us the differential equation of y of t with respect to t, and that's equal to secant of y of t squared. That's all inside the secant. Maple says, let me think about it. Ugh. It's got something called root of, and then Fresnel. Indeed, Fresnel. He was actually a really famous physicist. Optics. He did a lot of work in optics and rays. Super famous for creating a type of lens that actually saved lots and lots of sailors' lives because they imported it into lighthouses. But he's also really famous as a mathematician for coming up with the solution of an integral. It turns out that this integral is really nasty. So sometimes we can't even do the integrals to be able to solve the separation of variables problem. Even though it's separable, that's no guarantee that it's going to be pretty. It's not going to be a nice solution. So solutions exist, but it ain't pretty. And by the way, if you want to see what that integral looks like, how you'd go about doing that integral, here's a link to a YouTube video that you can check out. It's kind of interesting. I'll probably put a link to it in the notes list, the playlist, if you really want to watch it. If you're looking for something to help put you to sleep. So it turns out that there are some major issues. And so to kind of recap where we were at the beginning of the previous page, sometimes we have the issue that we can solve the general solution, but the general solution doesn't guarantee that we're going to see all the obvious solutions. Sometimes those equilibrium solutions are hiding in plain sight. The second problem that we ran into is sometimes things are just not separable. And so they're solvable, but we don't have the tools to do it. And then we found out that, yeah, sometimes things are separable and you can do the integration, but then you can't actually write things in explicit form, at least not in a way that makes sense. And last but not least, sometimes things are separable, but you can't even do the integration because it's really complicated. So just because we have this wonderful tool of the separation of variables doesn't guarantee that we're going to make sense out of what's going on. The last thing we're going to do for this video, before we jump into our application problem in the next video, is to take a look at our old pal, the exponential growth and decay, the population model from before. And if you remember, we kind of waved our hands in section 1.1 to get a solution. But what I want to do now is actually show where that solution comes from. And by this point in time, it shouldn't be too tough for you. So because of this thing being a separable differential equation, we can rewrite this. I'm going to leave the k on the right-hand side. And so this becomes the integral of dp over p equals, the other side is now the integral of k dt. By the way, it works if you move the k to the other side as well. It's just a little clunky because it's in the denominator. So I can integrate both sides. This becomes the natural log of the absolute value of p plus a constant. The right-hand side becomes k times t plus another constant. Now I'm going to solve this thing for p by getting those constants to the side and exponentiating. If you remember, e to the natural log of p becomes just p. And we don't have to worry about the absolute values because when you exponentiate, everything becomes positive anyways. So the right-hand side becomes e to the kt plus this third constant, c3. c2 minus c1 is the same thing as c3. And we use that rule for exponentials and say, hey, we've got a power that's an addition, so we can split it up into two things as a multiplication, and we get our solution, our general solution, which is e to some constant c3, which is just a constant, so I'll call that c4, times e to the kt. And so, just a reminder, c4 is equal to e to the c3 power. And that's where our solution from before came from. Our solution said that if you want to know the population at any time, you need to have some constant, which turns out to be the initial population, times e to the growth rate times t. And so that's where our model came from that we were using in section 1.1. So that gets us to the end of the kind of the meat and potatoes part of this. Now we're actually going to see some applications. The next video we're going to start off in dealing with applications. The last thing I want to show you for this one though is that if I ask Maple to solve that differential equation that we just saw, so if I say dsolve diff and I do p of t comma t, and that's equal to some constant k times p of t. Notice what Maple does when I say I want you to solve it. I didn't tell Maple that k is a constant, but watch what it does. It treats it like a constant. It treats it like some parameter, because if it's not a function of time and it's not named in the differential over here, then it's just going to treat it like a constant. So when we're dealing in Maple, Maple can handle dealing with things in symbolic form, which is really handy. It's nice for solving problems. Even if you don't have numbers, you can treat them as parameters. So that gets us to the end of this video. The next video will start up with our application, our mixture problem application.